Using both discs in conjunction with one another, example 2. Computing a perpendicular attack course to the target and computing optimum speed to put your boat 500 meters off the target's track for the torpedo shot. In this example, let's use the same target facts as the previous example. That is, let's assume the target is going on a course of 095 at 6 knots. We are approaching the target from the target's port side. The first thing we'd like to do, assuming we want to set up what's called a fast 90 attack, is to set our own course perpendicular to that of the target. So this is simple. On the front side, we simply set the target course, as we know how to do, to 095, and then we align the bow side of the attack course pointer here with the red line at 90. The red line is what we align with because we know we are looking at the red side of the target, that is the port side of the target. So we look at the attack course side, that's pointing to a course of 185. 185 will put us on a perpendicular course to the target. That is our perpendicular approach course. And so let's rotate the compass rose disc such that 185 is opposite the white triangle to set our own course, like so. And let's assume for this example that after we've turned, we have determined that the target is on a relative bearing of 60 degrees at 3,000 meters. So let's set that now on the attack disc. Firstly, we need to set our target course again. Since we moved the compass rose, we set that there. And then we set the bearing to 60 degrees, like so. And we read the angle on bow there of 30 degrees left. Let's note 30 degrees down, and we'll also note 3,000 meters because that's the range we measured. So now we go to the reverse side. We want to place our boat 500 meters off the target's track by the time the target gets up toward our bow when we're ready to shoot. I say 500 meters, but really any figure could be used, as long as it's not below, of course, 300 meters or whatever the arming distance is of the torpedoes you're firing. 500 meters is a good close range shot that will eliminate any estimation errors in the target data. And so, the first step is to figure out, based on the target's current bearing and its range, how far the target needs to travel in order to get to our bow. That calculation is very simple. We simply align the current range with the 90-degree mark on the angle disc. So we use the pointer for reference and align 3,000 with 90, and we know the bearing is 60, so we rotate the pointer and read off at 60 a distance figure of 2,600 meters. The target needs to travel 2,600 meters to cross our bow. We know the target is traveling at 6 knots, and so since we know the speed figure of the target, we set the pointer to it, like so, and we read off at 2,600 the time figure. As you can see, that reads 8.45. Now common sense dictates that that is not 8.45 seconds, it's not 84.5 seconds, it is in fact 845 seconds. The minute figure, if you're curious, is just over 14 minutes. However, we don't necessarily need to translate it into minutes in this case. Let's just note the seconds figure down of 845. We'll need that later. So we know the target is going to take 845 seconds to get to our bow. The next logical step is we need to figure out currently how far we are off the target's track at the moment to know how fast we need to go in 14 minutes, or 845 seconds. So we know that the angle on bow currently was 30 degrees. We know the momentary range is 3,000 meters. And so we keep the 3,000 all aligned with 90. It already is there, like so. And we read off at the angle on bow figure of 30, the distance to track. We are currently sitting 1,500 meters off the target's track. Now, we want to be 500 meters from the track, so we must subtract 500 meters, which gives us, of course, a distance to travel in 845 seconds of 1,000 meters. The final step of the calculation is to determine what our speed should be based on a distance of 1,000, 1,500 minus 500, and 845 seconds. This is simply a function of rotating the 845. We could use either 84.5 or 8.45. Let's just use, because it's closest to 1,000, the 84.5 figure with 1,000, and we read off at the speed disk a speed of what looks to be 23 knots. Well, we know that's not true. We have to correct the decimal place to 2.3 knots. We have to set 2.3 knots as our own speed in order to arrive 500 meters off the target's track when the target is roughly at our bow. Now, of course, as we know, the target won't be pointing directly from our bow, out from our bow at 0 degrees if we want a 0 degree gyro angle. So therefore, it may be 10, 15, depending on the target speed, off from our bow. Very simple, immaterial range difference. Just go with 500 meters, or if you'd like, bump it up maybe by 50 meters or so. One thing to note is if you grossly miscalculate this, of course, and are either going to be too far away, or worst case scenario, you end up beneath 300 meters at the time of the shot, you would simply increase your speed such that you run on the opposite side of the target's track for a stern shot. In that case, just instead of subtracting 500, you would calculate it such that you would arrive at the other side of the target's track at 500 meters. So in that case, you may just add 500 meters from your distance to track in order to compute the speed you need to run to the other side of the target, so you don't shoot beneath your minimum arming range of your torpedo for a bow shot, for example.